So the aim of this podcast is to give you some practice in calculating problems with collisions in mechanics. And in these problems here, there are going to be two parts, and the first part we are going to use this notation here. So we have two objects, we can think of them as balls. This has got mass m1 and initial velocity u1 in this direction, and it's going to strike a particle of mass m2, initial velocity u2, and afterwards the masses are unchanged, but the velocities are going to be v1 and v2 respectively. And in the first question, you are to assume that this is an elastic collision, that these are the masses of the two balls, and that these are the velocities of the two balls before the collision. In other words, here this ball is at rest, and your mission is to find the final velocities after the collision, v1 and v2. The second question is assume now that for exactly the same problem, the same masses and the same initial velocities, that this is an inelastic collision and that the coefficient of restitution E has value 0.8. And again, find V1 and V2. To solve these problems, you may use this formula here for the final velocity V1 in terms of the other parameters, and from this formula you can immediately write down by symmetry what V2 is going to be just by swapping 1 and 2 around everywhere here. And remember, for an elastic collision the coefficient of restitution is 1. And then finally for part A, as a more theoretical problem, I'd like you to try to rederive this equation in the elastic limit, so the E is 1 case, from conservation of kinetic energy and conservation of momentum. So what I'd like you to do is to write all of this down on paper and pencil, and then try to do the problems, and afterwards you can come back, and the next step in this podcast is going to be the answers, and then there will be a problem on part 2 as well. So have a go at doing the problems before you look at the solutions. Okay, welcome back. Let's, on the next slide, look at this problem and find the final velocities. Okay, so here we have the problem to look at. It's an elastic collision. We have this particle of mass 2 kilograms with initial velocity of 5 meters per second in this direction, hitting a particle of mass 3 kilograms which is stationary, and we are asked to calculate the velocities of the two particles after the collision. So the formula, which was stated on the very first slide, is given again here, and this is a formula for the velocity v1, and here we have a difference of masses times an initial velocity. Here we have got a geometric number times a mass times a velocity, so the units of these terms are kilograms times meters per second, kilograms times meters per second, and in the denominator we have a sum of masses, so the units of the denominator are kilograms, so overall we see that the kilograms cancel, and as we would expect, the units of this side are meters per second, and that gives us some justification for hoping that this formula is correct, and we will derive it in a few minutes. So all we have to do is put the numbers from this side of the problem, what happened before the collision, into this equation, and it gives us the answer. So m1 minus m2 is 2 minus 3 times u1, which is 5, and then we have plus 2m2, which is 3, times u2, which was 0. So this term will vanish. Here we're going to have minus 1 times 5, so that's minus 5, and on the bottom we have the sum of the masses, 2 plus 3, so that's 2 plus 3 is 5. The 5's will cancel and we'll be left with minus 1. So the answer for the velocity v1 is going to be minus 1 meters per second. And what that corresponds to is that the particle, when it hits this, rebounds and it moves backwards. So what about v2? Well, from this expression, we can immediately write down the equivalent expression for the velocity v2. All we have to do is everywhere where we have a subscript 1, we replace it by a subscript 2, and vice versa. So v2 we get from replacing 1 by 2. Here we have not m1 minus m2, but m2 minus m1 times u2 plus 2, geometric number, times not m2 but m1, not u2 but u1, and on the bottom we have m1 plus m2 will go to m2 plus m1, but that's exactly the same thing, so I'll just write m1 plus m2. So that is the equivalent expression to this one, and the units will work in exactly the same way. So the velocity v2 is going to be given by now. m2 is 3 kilograms minus 2 kilograms times u2, which is 0, so that's going to vanish, plus 2 times m1, which is 2 kilograms, times u1, which is 5 meters per second. So that's going to be 2 times 2 is 4 times 5, and on the bottom we again have 5 kilograms, m1 plus m2 is 5. So the 5's will cancel and we'll get 4 meters per second. So that's the answer for V2. Now, whenever we can check our work, we should. And here there is a very nice way of checking our answers. And this is to use something called the velocity flip. So there is a relative velocity initially, say it is u1 minus u2. And after the collision, what happens is you have exactly the same thing but swapped around. So instead of u1 minus u2 being the same as v1 minus v2, it's the same as this with a minus sign, and that's v2 minus v1. So the relative velocity changes direction. That's what this equation here gives us. And this gives us a very simple numeric, and this is true, by the way, in the elastic case. So this is true, and we can just put the numbers in. So over here, v2 minus v1, we're going to have v2 is 4, minus, and then v1 is minus 1. 4 minus minus 1 is 5. And on this side, u1 is 5, minus u2, which was 0. So we indeed obtain 5 meters per second is equal to 5 meters per second, and that works as expected. So we conclude that the check indicates that we have not made a mistake, and these are our answers for the two velocities in this elastic collision. So with that, I'm going to move to a very similar problem for an inelastic collision. So for an inelastic collision, and I'm going to be taking here that the coefficient of restitution is 0.8, and this is dimensionless. We have the same diagram, and I've taken the same initial values, and the equation that we had before, if we have an inelastic collision, is replaced by this one. And if we look at this, we see that as e goes to 1, which is the elastic case, we would have m1 minus m2 that we had a moment ago, and 1 plus 1 would be 2. So this reproduces what we had a moment ago for e equals 1, but this is a more general equation that works for inelastic collisions. So all we have to do is again put the numbers in. So to calculate v1, we have m1, which was 2, minus e, which is 0.8, times m2, which was 3 kilograms, all multiplied by u1, which was 5, and then we add to this, 1 plus the coefficient of restitution, that's 1 plus 0.8, which is 1.8, times 2, the mass m2, which is 3 kilograms, times u2, which is 0, so this will vanish. And on the bottom, we still have the sum of the masses, m1 plus m2, and that's 5 kilograms again, so the 5s will cancel, so we have 2 minus this, which is 2.4, so we get overall minus 0.4 meters per second, and that is the value of the velocity of this 2 kilogram mass after the collision. So it's again rebounded, and that's what the minus sign means, it's changed direction. But a moment ago its velocity was minus 1 meters per second after the collision, and now it is slower. And that's because energy has been lost in this, kinetic energy has been lost in this inelastic collision, and that's why it is moving more slowly. Again, by symmetry, we can write out what V2 is just by swapping 1 and 2 around throughout this equation, and again notice that m1 plus m2 when we swap 1 and 2 around becomes m2 plus m1, but that's the same thing as m1 plus m2, so I've just written it this way again. Again, we put the numbers in. u2 we remember vanished, so this term is 0, I've just put it straight to 0, plus 1 plus 0.8, so that's 1.8, times m1, which was 2 kilograms, times u1, which was 5, and that's that, all divided by 2 plus 3, so 5 kilograms. The 5's cancel, 2 times 1.8 is 3.6 meters per second, and that is the velocity of this particle after the collision. And again, we notice that the velocity here after the collision is less than we had a moment ago. A moment ago this was 4 meters per second in the elastic case, and again we see kinetic energy has been lost. And we can check this again. Now in the inelastic case we do not have an exact velocity flip, but in an equation which goes back to Isaac Newton we have a velocity flip but with a reduction factor, which is the coefficient of restitution here. So we just put this 0.8 in here, and I would ask you just to verify it, and what you will see is that on both sides you are going to end up with 4 meters per second, and again that gives us the idea that what we've written is, or what we've calculated is probably correct. I mean, checking something like this does not rigorously prove it's right, but it gives us that sort of happy feeling that we think we're right, and if we'd made a silly mistake, with a bit of luck this would spot it for us. So with that, I'm going to move on to actually deriving this equation, but in the elastic limit. I'll do that on the next slide. So on this slide, what I want to do is to derive the formula for the velocity of a particle after an elastic collision between two particles in one dimension, and this is the formula that we're going to eventually reach. So we're going to start with a fundamental property, conservation of momentum, written here. The momentum is the mass times the velocity, so this can be negative here. So it's m1u1 plus m2u2, that's the total momentum before the collision, is equal to the total momentum after the collision. So that's a fundamental property. Conservation of energy is also fundamental, but what we're going to do now is an approximation. We're not going to say that just energy is conserved, we're going to say that kinetic energy is conserved, and if we're in a situation where that is close to the truth, we talk about it being the elastic limit. So this is an approximation. The kinetic energy is the sum of half the mass times the speed squared, so these are positive terms. So that's the kinetic energy of particle 1 plus kinetic energy of particle 2, and that total kinetic energy, we say, is the same after the collision, so it's a half m1v1 squared plus a half m2v2 squared. A classic example of the elastic limit where it's widely used is, say, the collision of two billiard balls, but there we can see that it's an approximation, or better, we can hear that it's an approximation, because if you're playing snooker or pool and two balls collide, there is normally an audible click, and that sound that you hear is energy being carried away in the form of sound energy, vibrations in the atmosphere. So conservation of kinetic energy is an approximation, it's not exact. So these are our two equations, and what we want from them is to get v1, the velocity of one of the particles after the collision, in terms of the masses and initial velocities of the particles before the collision. So we want, in other words, to get rid of v2. To do that in the most elegant way, what I'm going to do is I'm going to take equation 1 and put together on one side all the terms with the mass m1, and on the other side all the terms with the mass m2. So here we have m1u1, and I'm going to subtract m1v1 here from it, giving me this, taking out the common factor of m1. And on the other side, we're going to have m2v2 is already there, but we have to subtract m2u2 here, so that's m2 times v2 minus u2. So all this is the law of conservation of momentum rewritten in such a way that the m1 terms are on this side and the m2 terms are on this side. In a similar way, we take our approximation, the conservation of kinetic energy in the elastic limit, and we are going to do the following. First of all, we see that in this equation every term is multiplied by a half, so let's just multiply the entire equation by a factor of 2 and get rid of these factors of a half. And then, having done that, let's bring together on the left hand side all the terms with m1 multiplying them. So there's an m1u1 squared, and we'll take this over to the other side, so we'd have m1u1 squared minus m1v1 squared, and that I've written here. On the other side of this equation are the terms with m2, so we have m2v2 squared, and then we subtract from it m2u2 squared, so that's this. Now here we have differences of squares, and there is a well-known, very useful algebraic identity that the difference of two squares, say a squared minus b squared, can be written as a minus b times a plus b. So in that way we can take this equation here, m1 just sits there, and u1 squared minus v1 squared becomes u1 minus v1, that's like this, times u1 plus v1. And on the other side we get m2 times v2 minus u2 times v2 plus u2. So now we seem to have done a lot of work. What's the point? The point is now we look at this equation here and we recognize that when we'd written equation 1 we had m1 u1 minus v1, which is this term, is equal to m2 v2 minus u2, which is exactly this term. So this is equal to that, and therefore we can just cancel those equal common factors on both sides. It's like a moment ago when we had the halves everywhere, we got rid of them. In the same way we can get rid of this. So what we now see is u1 plus v1 is v2 plus u2, and that is the equation that we were looking for. I've just written it out explicitly without this stuff, and it gives us v2 in terms of the other three velocities. Before we use it to get our final result, it's worth perhaps rewriting this in a slightly different way. So I'm going to rewrite this as the difference of the final velocities, v1 minus v2, bringing that over to here, is equal to, and then it's u2, and I'll take u1 over here, so it's u2 minus u1. So what we see is that the difference of the velocities after the collision, v's being the final velocities, is equal to the difference of the velocities before the collision, but you see that there is a minus sign difference. This is v1 minus v2, this is u2 minus u1. So 1 and 2 are swapped around. And this is what we call the relative velocity flipping. So there is a change in sign. They have the same relative speed before and after the collision, but the direction of the relative speed, or the direction of the relative velocities, better said, has changed. It's flipped. Okay, having said that, let's get back to this equation here, and I'm just going to rewrite v2 as u1 plus v1 minus u2. So that's our equation here, and now we can just substitute this into our equation for the conservation of momentum, and in this way I can get rid of v2 and rewrite it in terms of the other three velocities. So this side has not changed, it's m1 u1 plus m2 u2 is equal to m1 v1, and then m2 multiplies into all three of those terms, so it's m2 times u1 plus m2 times v1, and then it's minus m2 times u2. So now, we want to have v1 in terms of the other velocities, so I'm going to put together the v1 terms. There are two of them here, and v1 is multiplied by m1 plus m2, so I'll pull that out as a common factor. And then if I leave these two terms on this side and I take the others over, I would have m1 u1 plus m2 u2 minus m2 u1 and then plus m2 u2. So we've got m2 u2, and when this comes over it's going to double it. So we're going to get 2 m2 u2. And the m1 u1 term, we subtract an m2 u1 term from it. So we get a difference of masses, m1 minus m2, all times u1, plus the sum 2m2 times u2. So that's essentially our result, and to finish it off we just divide both sides by m1 plus m2, and this gives us our final result. This is just this equation with both sides divided by m1 plus m2. So in a similar way we could have found v2, but there is no point going to all that trouble because this initial equation is symmetric if you swap 1 and 2 around, so we could just by symmetry immediately say that v2 is equal to m2 minus m1 all times u2 plus 2 times m1 u1 divided by m2 plus m1, which is the same thing as m1 plus m2. So the equation for v2 is immediate. Before we move on, I'd like to say I think things like this take some time to understand, and it's really worth having, if you don't find this immediately easy, having another go at it on a sheet of paper and trying to do it by hand and then see if you understand it with time. That's how people understand derivations. So with that, we'll move on to the next question. So in the final part of this quiz video, we're considering an object, a ball, coming in, and it's going to collide off the wall and bounce off in an inelastic collision. And the way we see it's an inelastic collision is because these two angles are different. So this is 45 degrees and this is 30 degrees. So what I'd like you to do is to find out from this what the coefficient of restitution E is equal to for this problem. And you may notice that I have not said what the initial and final speeds are, and what you should be able to see is that knowledge of the angles alone tells you what E is. So again, I suggest you try to do the problem, and then you can use the answer on the next slide to see if you've got it right. So with that, I suggest you use pen and paper, write things down, and come back in a moment. Okay, welcome back. Let's look at the answer on the next slide. Okay, so to solve this problem, I think the easiest thing to do is first of all to redraw the diagram, but mark in some additional angles. So this angle we were given, it's 45 degrees, so if we drop a perpendicular towards the wall, then since these angles have to add up to 180 degrees, and that's a right angle, this is also 45 degrees. And then since the angle's in a right angle here, this line is parallel to the wall, this is perpendicular to it. Since the angle's in a right angle, I have to add up to 90, this is also 45 degrees. Similarly here, if we look at the angle this line makes with a line parallel to the wall, it's 30 degrees, and that means that the angle this line makes with a line at right angles to the wall, it's going to be 60 degrees, so these two angles add up to 90 degrees. And what I want to do now is I want to introduce unit vectors, and when I do that, I'm going to say that my unit vector perpendicular to the wall is going to be I, and my unit vector along the wall in the direction of motion is J. So this velocity vector can be split into a term at right angles to the wall in the I direction, and a term along the wall in the J direction. And after the collision is against the wall, so it bounces back, so the component of the velocity vector after the collision in the I direction is now going to be negative, and the component along the wall in the J direction is going to be positive, and it's also going to be exactly the same as it was before the collision, because there is no force along the wall. The force of the collision is in the I direction, and to be more concrete, more precise, it's in the minus I direction, it's in that direction. So you can solve this problem either by using components or by using vectors. I'm going to use vectors, both will work. So I'm going to give the velocity before the collision the name u. So I'm going to just annotate my diagram here. I hope this isn't getting too complicated, with u as a vector, and after the collision with v as a vector. So the velocity before the collision, u, is going to be the speed, u, times, and now I want to be looking at the component in this direction, so it is the velocity times the cosine of this angle, so it is u times the cosine of 45 degrees. And that is in the I direction, and in the J direction we're going to have the speed u times the cosine of this angle here, and that's 45 degrees as well. So this is being broken into this, u the vector times the cosine of that angle, and this times u the vector, or the magnitude of it, times the cosine of that angle. So it's also u cos 45 j. And similarly, after the collision, v is going to be the magnitude of v, so let's call that little v. And now let's go back to the diagram. We're looking in the I direction, and it's bounced back this way, so there's going to be a minus sign, and it's going to be the cosine of that angle. So I'll put the minus sign in, and it's the cosine of 60 degrees in the I direction, minus sign saying it's rebounding from the wall, plus, and then it's V, and now again going back to the diagram, it's going to be the magnitude of this velocity, in other words the speed, times the cosine of that angle to work out this component. So it's V times the cosine of 30. So it's V cos 30 J. And both of these velocities have units of meters per second. And again, let's just note that U is the magnitude of U and V is the magnitude of the vector V. So we had to introduce these velocities U and V, and in the end the speeds U and V that we have here and here will end up cancelling. So our equations now are that along the wall there is no acceleration. That's our first equation, so let me write that down. Our first equation, I've just written it here, is that there is no acceleration along the wall, and that's in the j direction, so that tells us u cos 45 is equal to v cos 30. So let me just write that down. U cos 45 degrees is equal to v times the cosine of 30. And what about at right angles to the wall? Well, at right angles to the wall, the ball is going to bounce backwards, but it will not have the same component of velocity with a minus sign. It's going to be reduced by a multiplicative factor of e, the coefficient of restitution. So let's just write that down. So perpendicular to the wall we've had a velocity flip, but afterwards the velocity is going to be the velocity afterwards is going to be the initial velocity with a minus sign because of the flip, but multiplied by a coefficient of restitution, which normally is less than 1, normally means that the velocity at right angles to the wall is reduced compared to the component of the velocity at right angles to the wall beforehand, forgetting about the overall minus sign. So that tells us the following. It says that afterwards, I'm going to look at it the other way around, we have that V times the cosine of 60 degrees, that comes from here, V times cosine of 60, that's in this direction, is equal to, and it's minus because it's changed direction, and there is E, this multiplicative factor we mentioned, and then it is U times the cosine of 45 degrees, because if we go back to here, U cos 45 is the component of the velocity in this direction. So now we've got two equations, and what we're going to be able to do is we can rewrite V in terms of U here. We can then substitute V here in terms of U, so we'll have U on both sides, which will cancel. That's why our answer is not going to depend upon the speeds. And then we're going to have these geometric numbers, these cosines here and E, and that will tell us what the value of E is. And sorry, I should have put a minus sign here, because this is what we have here, minus v cos 60 in the I direction here, and it's going to be equal to this. So this is just the idea that we are replacing this v cos 60 by EU cos 45. So let's now just work out what these values are. These are all nice angles that I've chosen deliberately. We know that the cosine of 45 degrees is 1 over the square root of 2. We have that the cosine of 60 degrees is equal to a half, and we have that the cosine of 30 degrees is the square root of 3 divided by 2. These are all values that you can check by looking at simple right angle triangles. So if we go and look at this equation here, we can rewrite it as follows. We can say that v cos 30 is equal to u cos 45. I've just swapped the sides around. So that tells us that v times root 3 over 2 is equal to u times 1 over root 2. And that tells us that v is equal to, so now I multiply both sides by 2, so I'm going to get 2 over root 2 on that side, and 2 divided by root 2 is the square root of 2. And then I'm going to divide both sides by the square root of 3, so that means that on the bottom here, on this side, I'm going to get a factor of the square root of 3, and that's all multiplying u. So now I know what v is in terms of u, purely because of the angles that were here. Now I look at the second equation. The minus signs will cancel, so we don't need to worry about those. That becomes plus, that becomes plus. I'm going to swap the sides around so that I have e on the left-hand side. So we have e times u times the cosine of 45, which is 1 over root 2, is going to be equal to v times the cosine of 60, and the cosine of 60 is a half. So this tells us that e times u is equal to v, and then it's the square root of 2 divided by 2. So now what I can do is I can replace v here by u using this equation, cancel the u's, and we'll obtain our result for e. Before I do that, by the way, I should have perhaps commented that if I look at this result here, I'm expecting after an inelastic collision that the speed normally is less after the collision than before the collision. And that's exactly what we get here. V is u times this number, and root 2 divided by root 3, well, that ratio is less than 1. So the ball in the collision has slowed down, as I would expect. So this is making us feel we haven't made any obvious mistakes. So we put this now into here, and what we obtain is the following. We have e times u is equal to, and v here is root 2 divided by root 3 times u, so it's root 2 divided by root 3 times u, and then we have this factor here of root 2 over 2, So let's put it there again. And now when we look at this, we see we've got root 2 times root 2, but that's 2. We've got a 2 on the bottom, so these terms here, root 2 times root 2 gives us 2, which cancels with that. So that's very nice. And then we also have, as promised, that the u factors on both sides cancel. So what we obtain is that e, the coefficient of restitution, is going to be, well, in the numerator, everything's cancelled, so we're left with 1 divided by the square root of 3. The coefficient of restitution is a dimensionless number. It has no units. And to two significant figures, according to my calculator, this means that E is 0.58 to two significant figures. Although I must admit that I personally prefer leaving it as 1 divided by the square root of 3. So I hope working through this quiz video has been useful to you and given you some practice and some feedback on what you understand and what you need to practice further. I'll stop here.